Welcome to our video on understanding solubility. Before you watch this video, you should already have watched Tyler DeWitt's YouTube video on the differences between ionic and covalent things dissolving. Now, we already know our solubility rule from Chem 1 that likes dissolve likes, meaning that if we try taking a polar solute and dissolving it in a polar solvent, that they should dissolve, as well as nonpolar and nonpolar should dissolve. But if we try to mix something polar with something that is nonpolar, we know they will not dissolve. But why exactly is this so? Well, to understand this, we need to understand some differences. Now, from the video, you should have seen that when ionic substances dissolve, they separate into individual ions. And if you have a polyatomic ion, and this was not shown in the video, remember, a polyatomic ion is one that has atoms covalently bonded in a group to make an ion, such as nitrate. You have nitrogen atoms and oxygen atoms covalently bonded to each other. When you dissolve something like potassium nitrate, the potassium separates from the nitrate, but the nitrogen and oxygen are still covalently bonded together. Those do not break. However, the ionic bond between the potassium and the nitrate does. When covalent substances dissolve, the molecules separate into individual molecules. There are no covalent bonds that are broken. The only thing that is broken are the intermolecular forces. Now, in the ionic solution, you're going to have a solution that conducts electricity because those ions are electrolytes in there, and the charges will be able to carry and to conduct an electrical circuit. Whereas with a covalent, you do not have any ions, just molecules which do not have charges. They're neutral, so there's no electrolytes in there. Another thing we talked about in Chem 1 was the difference between true solutions and colloids, and the difference is size. In a true solution, your substances are separating and dissolving into individual ions or molecules. In a colloid, they're not breaking down apart that completely. You're just getting clumps of molecules. So in a true solution, the size is about less than a nanometer in size. We're talking about atoms and molecules, and those are less than 1 nanometer. In colloids, we're talking about clumps of molecules, so we're looking at between 1 to 1,000 nanometers. When you look with your eyes at a true solution, it appears homogeneous. Also, if you were to look at a true solution with a microscope, it would appear homogeneous because the particles are too small even to be seen by a microscope. If you were to look at a colloid with your eyes, it appears homogeneous because the clumps are still too small to see with your eye. However, most colloids, you would be able to see the individual particles with a microscope, so it would appear heterogeneous at the microscopic level. In a true solution, if you shine a beam of light, such as a laser, through them, the particles are so small that you won't be able to see the beam at all. It will not scatter the light. But in a colloid, the particles are large enough that the light will bounce off of them and it will scatter the light, and you will observe what's called a Tyndall effect, like we've done in class with the laser beam. If you try to separate a true solution by passing it through filter paper, you're not going to have any luck because all of the particles are so small they'll go right through the filter paper. If you try to separate a colloid with just regular filter paper, well, that's not going to work either because those clumps are still too small for regular filter paper. But if you got some special parchment paper or membrane where the pores are even tinier, that would be able to separate a lot of colloids because the particles would be too big to pass through those. A true solution, even through parchment paper or the membrane, will pass through, so you won't be able to separate a true solution either way. Now, we really want to get to what happens when something dissolves, what forces are involved. And we have several situations here. We can have ionic compounds dissolved in polar solvents, we can have polar things dissolved in polar solvents, or we can talk about mixing two nonpolar things. So we're first going to look at ionic things. Here we have a typical ionic compound, potassium and chloride. They're held together because the ions have opposite charges. However, when we put this in water, things get a little more complicated because the ions are also attracted to the dipoles of the water molecules. So here we have our chloride ion. Well, it's going to be attracted to the positive end of the water molecule. Water's polar, of course, so we have our dipoles, and really that's a partial positive charge. And because there's an attraction between the two, we call it an ion, which the chloride is, to a dipole attraction. And if that attraction is strong enough, then we might be able to pull the compound apart. Of course, potassium chloride, potassium things all being soluble, that is able to pull apart. It depends on what attraction is stronger. Was the potassium more attracted to the chloride, or is the potassium more attracted to the water? And in this case, it's more attracted to the water, so it dissolves. So whenever you have an attraction between an ion and a polar molecule, it's called an ion to dipole force. And it's a comparison of which force is stronger about whether it will dissolve or not. Now we'll try watching this video. And in this case, we have a grain of salt getting put in water. You can see our water molecules coming in. They're surrounding the ions, and they're gradually pulling apart this grain of salt until we have individual ions just floating around in the water. And you can see these individual ions are getting surrounded by the water molecules. They're lining up so that the charges are attracted to the opposite charges, and we end up with these kind of clumps of water molecules with an ion at the center. Now we'll look a little more closely at that here. This process where the solvent comes in and surrounds the solute and dissolves it is called solvation. Specifically, whenever water is the solvent, it's called hydration. So here we have an example of a hydrated sodium ion. You can see it's been surrounded by water molecules. They've come in and they've dissolved it. Maybe this was salt. Now if we look closely, it's kind of interesting here because we have different forces at play with our water molecules. In some of these water molecules, the ones that are immediately surrounding the sodium ion, there's an ion to dipole attraction holding these water molecules to the ion. Now we have other water molecules here that are just surrounded by other water molecules. So there's hydrogen bonds that are holding these together. So it's interesting that not all of the water molecules are the same here. Some of them are held very tightly in place by those stronger ion to dipole forces. So this whole thing is called a hydration shell, and this all stays together as a clump of particles. So when you see the animations of an ionic compound dissolved in water, and when you just see the individual ions floating around in water, that's really not 100% accurate. Each individual ion is really surrounded by a shell of water molecules, and they move together as one whole unit through the water. Now these other water molecules, they're free individual molecules, free to move around as they are. Now because our ion is surrounded by this shell, this barrier of water molecules, if it were to bump into another, say, chloride ion, well, that also has a protective barrier of water molecules around it. So the likelihood of those combining together and reforming, it helps prevent that from happening. Now what if I have something polar and I'm trying to mix it with a polar solvent such as water? So here we have methanol and water, and both of these guys are very polar. In fact, we can see that we have a super dipole because each of these has a hydrogen bonded to a phone. In this case, it's both oxygen. And so we have this super dipole in both of these molecules. So if I mix these two things together, are they going to be attracted to each other? Well, of course they are, because there's going to be a hydrogen bonding that occurs here because of your super dipole to super dipole attraction. And that's going to be very comparable to the hydrogen bonding within the water molecules. So whether this molecule of water is attracted to another molecule of water or whether it's attracted to the methanol that we have here, it's all the same. It's all the same force. So they're easily going to mix and intersperse and dissolve with each other. Now what if we have other cases of polar solvents and polar solutes? Now here we have some cases where we do not have hydrogen bonding. The hydrogen is not directly bonded to a phone, so we just have regular dipoles. Are these guys going to be attracted to each other? Well, of course they are. But instead of hydrogen bonding attracting the one to the other, it's just going to be a dipole to dipole force. And again, this force is just as strong as the individual force. This molecule would be attracted to another molecule of itself because of the dipole to dipole attraction? Well, it's just as attracted to our solute here with a dipole to dipole. So yes, these guys are going to mix. These guys are going to dissolve in each other. But what if we tried mixing something nonpolar with something that is polar? Here we have some water molecules. Here we have a nonpolar ethylene molecule. Now, if we consider what's going on with the water molecules, these guys are all held together by hydrogen bonding, so they are very attracted to each other. On the other hand, we have our nonpolar ethylene, and since it's nonpolar, well, it is attracted to the water molecules, but it's a very weak attraction. It's just dispersion forces or maybe some induced dipole forces. So when it comes and tries to attract to the water molecules, well, they're so strongly attracted to each other that it doesn't let them in. You can think of water as a clique. It's like that group of school that just hangs out only with each other and they don't let anybody else in the group. So because of the hydrogen bonding, water forms this very, very tight clique. And unless something comes along that water is just as attracted to, it's not going to let it in and it's not going to let it mix. So we have no dissolving happening here, or no miscibility. That's just another fancy word for dissolving. So we all know, of course, that if we take oil, which is nonpolar, and combine it with water, they don't mix. We will get two separate layers. And again, that's why. It's not because the oil is not attracted to the water, it's because the water is just way too attracted to itself, and there's not a strong enough attraction to the oil to let the oil get in the clique. So we have just two separate layers. Now sometimes you'll hear people talk about oil and water repelling, and this is just not an accurate statement, because the oil is attracted to the water. It's just that that force of attraction is not strong enough to overcome these strong forces that are holding the water together. So hopefully you can see and understand a lot better why this saying likes dissolve likes works. It all has to do with the attraction between the solute and the solvent. Is that attraction just as strong as the attraction within the solute itself, and just as strong within the solvent itself? If I've got a polar solvent with maybe dipole to dipole forces, if I try to dissolve something in there, it needs to be polar, so there's at least a dipole to dipole attraction. If so, it will dissolve. So this is a good comparison here. So what type of force am I going to have in a solution? Depends on who my solute and who my solvent is. If I have an ionic compound dissolving in a polar solvent, I'm going to have ion to dipole attractions. If I have polar solvents and solutes, I could have hydrogen bonding if I've got a superdipole to superdipole attraction. Or if I just have regular polar molecules, I could have a dipole to dipole attraction there. Now, if my solvent is nonpolar, we can have a variety of scenarios. The only one we're really going to worry about here is if I have two nonpolar things. And this explains why these will mix with each other, because the dispersion to dispersion forces between the one solute and solvent is just as strong as the dispersion force within the solvent itself. And so since they're comparable to each other, they will mix and we get something that dissolves. Finally, I want to take a look at some larger molecules. We looked at some smaller, simpler molecules up to this point, where it's just got a polar side, where it's got a partial negative and a partial positive on it. But here's a little more confusing situation. Here we have some pentanol, or pentyl alcohol, and you can see we have an alcohol group, that OH there, which is going to be a polar end. There'll be a pretty large dipole on that because of the hydrogen bonded to the oxygen. So this, if we put this in water, the question is it going to dissolve or not? Well, that end of it is going to be attracted to my water molecules. It will actually hydrogen bond with the molecules. So we call that the hydrophilic end, or water-loving end, like Philadelphia, the city of brotherly love. Well, hydrophilic, loving of water. However, the rest of this molecule is all carbon and hydrogens, and so we can look at this as a nonpolar end. And so is this end of the molecule going to be attracted to water? Well, not very much. It's just going to have dispersion or induced dipoles that are trying to attract the water, and that's not going to be strong enough to get in there and mix it up with the water. So we call that the hydrophobic end. So we can imagine one end of this molecule being attracted to water, but the other end not. And since so much of this molecule has a nonpolar character, this guy actually hardly dissolves in water at all. And if we look at a variety of different alcohols like this, we have a very small alcohol, which is pretty much just all polar. There's hardly any hydrocarbons attached to that. So this guy would definitely be a very polar molecule. We certainly expect that one to dissolve very well in water. On the other end, we've got things as we are going down, we're getting bigger and bigger hydrocarbon ends. And so we have more and more and more of the molecule that has a nonpolar character to it. So if we tried putting these in water, we can probably guess that as we go down and get more and more nonpolar character, they're going to be less and less and less soluble in water. In fact, this hexanol down at the bottom is not considered soluble in water at all, even though it has this OH group and we predict hydrogen bonding. The rest of it is just so nonpolar, it's just not able to get in there and really mix it up with the water molecules. This is the same thing that's happening with the vegetable oil. We saw the formula for the vegetable oil having an OH group on it and thought, oh, we ought to have hydrogen bonds. Well, it's a much larger molecule even than this, and the majority of it is all nonpolar in character. And so, of course, we all know oil and water don't mix because of that just big, huge portion of it being nonpolar. Now, if we tried dissolving these guys in hexane, hexane is a nonpolar solvent. So our methanol up top, which is a very polar molecule, will not dissolve at all in hexane because the hexane attraction is not strong enough to break up the methanol's attraction to itself. But as we go down and get more and more nonpolar in character, we have our hexanol, which did not dissolve in water, very soluble in hexane because it's more nonpolar character than anywhere else. So hopefully that helps you to make some predictions and understand why things will dissolve in the types of things that they dissolve in.